Include machine learning and statistical inference, control and performance modeling and analysis of complex systems. Today, as his title suggests, he will be giving a talk about RLHF. Over to you, Aditya.
Hello, am I audible? Okay. Okay, good afternoon everyone. Welcome to this finale of this workshop. Not sure if it's going to be a grand finale. Yeah, so this is, I'm going to be talking about, something that is a preliminary take on a problem within this whole RLHF pipeline that you've already heard about in the previous talk, thanks to Vaneet. So it began with a very basic question that we asked and understood a little bit more about through our investigation. So I've titled it Strategically Towards Reliable Alignment, because there is no claim that we have solved any problems comprehensively. But hopefully I will be able to put in front of you, thoughts about, interesting problems that may arise in, these pipelines, modern pipelines where people are training large models, trying to fine tune them or train them further to achieve certain objectives that are claimed to be more aligned with human values and so on, right? So this is still a very, very emerging area. There are lots of interesting open questions, and hopefully this presents a case study for what sort of one could think about in this space, right? So just to sort of set the background for this, you've heard most of this already, again thanks to Vaneet, who gave a nice introduction to the whole process of large language models, how they are trained and how they are fine-tuned, and where RL enters specifically. But let me just recap this very quickly for our own understanding and in our own language for this talk. So a large language model is, at the end of the day, it's a special kind of neural network. What makes it special from previous neural networks like convolutional neural networks and so on is the presence of certain operations which are called self-attention operations. So a typical GPT or chat GPT kind of neural network will have tons of these self-attention layers. They do a very particular operation which is rumored to be behind the success of how they understand language and process it. Okay, so in any case, for our purposes, an LLM is a special neural network. It has a large number of weights which we will call using the vector theta. So the size of theta is, for example, in the size of billions or perhaps even trillions at this point. So what do you train it? How do you train these weights? How do you adjust these weights? Well, this neural network, which is the LLM, has the input representation as a sequence of tokens. You can just think of them as appropriately encoded strings of language. And given an entire sequence of strings at the input, which we call x, x1 through xn, the whole neural network is supposed to compute in one forward pass the probability distribution for only the next token or the next symbol or the next word in that which follows the stream of words or tokens. Okay, so p theta of xn plus 1 given x1 through n is supposed to be the probability distribution that the network predicts for the next word to follow. Okay, and that's the nature, that's the structure of this input output function, that is the LLM, parameterized by theta. The way you pre-train it, so there is this large, very intensive phase of training called pre-training, where you take a large data set of strings of some bounded size, let us say L. In principle, you can take the entire internet's worth of data and chop it up into sequential L length strings. That's literally what happens. There are actually very large text databases that you can actually download, which represent a reasonable archive of the entire internet. And then you chunk it up and then you prepare lots of these strings. And what you do is you essentially maximize over theta the following objective, which is you take all your chunks of data of strings and you just maximize the probability, the joint probability that your neural network, which is the LLM, assigns to all these strings. Okay, so that joint probability can be factorized into a product or sum of the log probabilities of the next token given the past and so on. But all in all, this is a very giant sort of log likelihood function that says help me increase the probability according to theta that the actual next token was seen in the data with respect to the previous tokens present in the data, right? So with respect to data, maximize the likelihood that my model assigns to these strings having been produced. Okay, so that is basically in one step, that's the definition at a very high level of pre-training. It requires a lot of engineering effort to do this. The length, the number of strings that you have as data is very, very large. So you need to actually do this maximization of this log likelihood very carefully over several passes, maybe in a distributed manner and so on. So that's what these big companies actually do. This is called pre-training. Okay, so the task here is to just match the probability distribution or the next token distribution of typical internet data. Okay, or text, English generated data. After this, we get into, what comes out of this pre-training is, this LLM neural network, which can reasonably reproduce or continue strings which have a distribution similar to what you see on the internet. That is often not suitable for many tasks that you might want to use the LLM for. So for example, you might want to use the LLM to answer questions for you. You may want to use the LLM to maybe do arithmetic calculations for you. You may want to use it to maybe give advice about which restaurant you want to go and eat, or what kind of cuisine you should experiment with and so on. So often based on whatever it has read or trained of the internet, the LLM is likely to sort of have certain undesirable qualities. It could be perhaps unfair to certain demographic groups. It could exhibit potentially, the tone could just not be right. It could be an angry tone or a very controversial tone and so on. So you'd like it to be a little more desirable, whatever that word means in the sense of applications. So what you do is you start with this pre-trained LLM, the LLM that just came out of the oven after pre-training, and you may want to sort of specialize this LLM a little more, that is to mess with these weights a little more, so that you think the LLM produces outputs that are a little more aligned with what people want in applications, right? So for example, a very common objective for LLM alignment is what is called being more helpful, honest, or harmless. Okay, so it may not be very helpful or honest or harmless. For example, a pre-trained LLM is very likely to go ahead and give you a recipe for making a bomb or some destructive weapon. Just because it has no idea of what implications that can carry. So you may want to make it a little more quote unquote responsible or helpful or honest or harmless, whatever quality you desire in the application. And one way to do this, of course a very naive way to do this, is to literally continue your pre-training with examples of strings of questions and answers that are of a desirable type, right? So for example, you may try to get what is called prompt response data. So if you want the LLM to maybe refrain from answering a certain question, like how can I make a bomb to blow up a building, you may probably want to collect lots of data of this type, saying this is the question and the ideal answer is sorry, I cannot help you with this, sorry, I cannot help you with this. Okay, so you may want to sort of nudge the LLM by implicitly getting lots of labeled data, more labeled data, which somehow have a signal of desired behavior, right? Either demonstrations of helpfulness, demonstrations of honesty, demonstrations of harmlessness, whatever demonstrations you like. Okay, unfortunately this is very hard to do. It requires a lot of effort to actually get people, humans have to write this data ultimately, right? Custom data, custom strings. It's difficult to for humans to actually come up with a lot of these example or gold standard prompt response data to demonstrate such desired behavior, right? So this is a very costly affair. Okay, however, it's much easier for humans to actually rate, or in fact even preferentially rate candidate responses to various prompts or various questions, right? So for example, if I have a question saying, can you help me make a bomb? I present you with two answers. One answer is, sorry, this is, a question that is fraught with danger. I cannot answer it. The other candidate response is, okay, sure, here you go, take this ingredient, take that ingredient, mix them these together and so on, right? A human finds it very easy to sort of judge and say, I prefer one to the other, right? So it's just a binary output that the human has to give. It's much, much easier and cognitively lighter for human beings to give feedback, to give preferential feedback of this form over pairs of responses, right? So pairs of responses for the same question, right? So, so that's sort of the reason why this RLHF really became popular, because companies found out that you could collect, in principle, if you could take lots of quote unquote controversial questions and generate candidate answers for at least two answers for each of these, you could then go to a human or a crowd of humans and ask them to sort of very quickly or effortlessly prefer one to the other, right? It's almost like an instinctive decision for a human to say, I prefer this over that. Okay, it doesn't take too much thought. It's much easier certainly than a human actually having to write an ideal response for a question. Okay, so think about it that way, right? It's much more intensive for you to think about writing an answer to a question. Okay, so that's sort of the nature of this preferential feedback that forms the basis of what is called alignment using preferences, or in short RLHF, reinforcement learning using human feedback. Okay, so we'll go over this in some more detail. So there are two steps in the classical way of sort of doing RLHF, which is working with these preferences that are gathered to actually improve the LLM model. So let's represent the human preference data that someone might gather as So as a data set where each data instance consists of a question which is QI, and then there are two answers called A, W and AL, which are assumed to be ranked. So the W is for win and the L is for the losing answer. So we assume that there is a large data set that has been efficiently collected in this way by asking humans, for question Q1, do you prefer one answer A1W or the other answer A1L? I mean, whatever comes first is put as the first entry of that data set, right? So the assumption here is that A1W is the preferred answer for Q1 compared to A1L and so on and so forth. Okay, so this is a large data set, not extremely large though. There are obviously limits to collecting such preference data. If you go to the internet, you will find sort of at least open source data sets where perhaps the number of preferences is of the order of 50k or 100k examples. Okay, so I think one can scale it up in modern times using synthetically generated preferences, but that's another story. Okay, but you should think of basically each of the QIs and the AIWs and the AILs as being strings. Okay, so let's just imagine that we are working over the space of language strings. Okay, so Q1 is an entire question, A1 is an entire candidate answer, A1W, and then A1L is also an entire candidate answer, which is just not preferred relative to A1W. Okay, so that's your data set. The big question is, how do you use such a data set at your disposal along with a pre-trained large language model, which we denote by the parameters theta 0. How do you make, from that theta 0 a better LLM that let's say we'll call theta 1 using this kind of data? Okay, there is no reward signal here, by the way. It's just a preference signal. It's very relative data. Okay, all it says is A1W is preferred to A1L for the question Q1. A2W is preferred to A2L compared for the question Q2 and so on, right? That's all the data you have. How do you sort of in some principled way try to nudge the LLM to prefer A1W over A1L, for example, for question Q1, okay? So there is a classical approach for doing this, and that one involves essentially inferring a reward function, an gathered. Okay, so for example, one would like that R of Q1 with A1W should be larger than R of Q1 to A1L, right? It should respect the nature of the data, right? So you would like to learn a scalar valued function R, which is somehow compatible with the very discrete preference data that you have to work with. Okay, so towards that, what is done is, you want to learn a function R. Let's just parameterize that R that we want to learn in terms of another neural network, okay, with some parameters mu. So what we want to learn is a function called R mu, okay. What you do is you literally do the same exercise, except that you have to use now a preference model in between to help express the probability that A1W beats A1L, okay, or Q1 A1W beats Q1 A1L, right? That one string beats another string, so that you can relate it to the actual discrete preferences that you express, right? So this is what was called the Bradley-Terry preference model, which you saw in the earlier talk. The Bradley-Terry preference model is a very simplistic preference model. It says that every object which is Q comma A in this case has a score which is a reward R mu of Q comma A, and we assume some generative model where if A and A prime are presented against the same question Q, then the probability that A will be chosen to be the winner is exactly the sigmoid of the reward of QA minus the reward of QA prime, right? So this is a very simple model. One can critique it, and ask. Likelihood problem where you want to really learn the underlying reward scoring function R mu, and you have this binary data that you assume have been generated by flipping coins according to these Bradley-Terry probabilities. Okay, so you train mu to maximize this thing, and at the end of this process, outcomes, or at least you're supposed to get a reward model which can help you score every possible question answer string, not just the ones in your data set. Okay, so in some sense the hope is that you have been able to learn some structure of what people prefer and what people don't prefer using the data, and now you have somehow magically a model, a reward model that can give you actually a scalar reward function. Okay, so what do you do when you have a reward function? The immediate instinct is to try and maximize it. Okay, so anyway, before that, this is a graphical schematic of this whole reward modeling process. You take, you collect question and answer, two answer pairs, and then you go to a crowd of humans and say, think about whether you prefer A1 or A2. In this exercise, often there's additional information that is supplied to the human respondents about, make sure you prefer, responses that are more helpful, more honest. There is some standard blurb that is given to them. In the hope that they don't completely go off track, and you try to sort of make them align to certain values that you expect will be reflected in the preferences, right? But in any case, these are preferences that are gathered from individual humans. This is part of data collection. Once you have a lot of such preference data for a bunch of questions and candidate pairs of answers, then you pass it through this what is called a reward modeling neural network. And you try to learn a map between any question answer combination and a scalar answer, which is the reward of or the score for that question answer, such that it is, it's sort of maximum likelihood with respect to the Bradley-Terry preference model, okay, that you assume for the data generation. So this is reward modeling in a nutshell. So this is just step 1. At the end of step 1, you have a way to, in principle, assign an importance to any particular answer for any particular question, okay. And the next logical step is, once you have a reward function, it makes sense to try to maximize the reward function, because that is what you learnt it for the purpose of. And so this is the RL part of RLHF. The HF part is really the preferential feedback part. The RL part is consists of taking this reward model that you've learned, the RMU function, and saying that, look, your LLM is an input-output function that takes a question and gives an answer. Imagine it as a very simple policy. In the RL language, it's a policy that maps states to actions. The states are the Qs and the actions are the As. And I now have a way to evaluate for any given LLM theta what is the expected quality of its output for a given input Q, right? So in expectation, if I have a distribution over candidate prompts Q, then I can talk about the value achieved by this LLM or the policy over, it's just a single number. It's the expected value of R mu QA, where Q is drawn from some default prompt distribution, and A is drawn according to the internal, probabilistic mapping of the LLM, the P theta, okay. And so this is a number that you can hope to actually maximize, okay, and then claim hopefully that you have gained an improvement over your previous LLM to a better LLM. You've gone from theta naught to a theta 1, which is hopefully a little more aligned because you have put in all this effort to nudge it towards preferred responses using this reward function, okay. So one other sort of important, technical but important constraint here in this problem is that you have your initial LLM theta naught. You don't want to really, move it too far from theta naught, in the sense that, one can try to just maximize the reward function that you got, but then there's nothing to say that this reward function is really useful, okay. It may have some amount of noise, or it may have some amount of inaccuracy, because ultimately you've learnt it from a few pairwise preferences. So there is this sort of standard wisdom of saying that, I will try to improve my policy from theta naught to a theta 1, but I will constrain the movement between theta naught and theta 1 to be not too large. I don't want to sort of undo all the progress I have had during pre-training. So I will try to just locally improve this policy in the direction of increasing the expected reward that I have learned. Okay, so that's the RLHF problem. And in a nutshell, it is this, that neural network on the left hand side that I have drawn is a representation of the LLM, which is theta, and you can imagine a hypothetical prompt being passed to it and a probabilistic response that it outputs. That response is evaluated on this trained reward model R mu, which scores it, and the aim is to basically improve the expected score from input to output. Okay, so you sort of do this, use this reward, and then you can somehow hope to tweak your theta in some principled way to make it achieve higher and higher expected reward. At the same time, you also have a penalty for moving too far, right? So that is always something in the background. Any questions so far?
Can you go back to the previous slide?
Yes, please.
So that means that expectation is with respect to theta.
The expected value is with respect to two things technically. It's with respect to Q being sampled from some default distribution.
No, but what's the probability distribution?
Q is sampled from some Px, okay, that's a generic prompt distribution.
Okay.
Imagine the distribution of prompts in the wild, for example, right? And once conditioned on Q, A is sampled from pi theta of, A is sampled from P theta of dot given Q, P theta A given Q. So the LLM uses Q and then probabilistically outputs an A. That's the P theta of dot given Q.
And same thing here, P theta.
Same thing here.
KL between P theta given Q and P theta.
Exactly in the same way. Yeah.
No, then this can be exactly solved. You will get this Gibbs kind of distribution.
So it can be exactly solved, assuming that all you have the tabular parameterization of policies, right?
Now, if you know the function P theta dot.
If you know the function
R mu,
P
sorry,
theta
R mu,
dot,
you need R mu. So P theta, let's forget Q, that's a fix.
Sure.
P theta will be P theta not E raised to R mu.
That's only if you assume that
Normalized, yeah.
you are in the tabular case. It's a parametric policy.
Okay.
It's not obvious that, it's not only in the full case you get the explicit Gibbs optimal solution. You're right. Okay, but that's, that is an assumption under which you will get that, yeah. You're right. But in general, it's P theta literally is an LLM parametric policy. It's not, it has a very specific architecture. So you have to optimize it within the constraints of that P theta. Right. So people will typically do, gradient descent. I mean, they'll use something like TRPO or PPO, which is essentially policy gradient over theta, which is the obvious thing to do.
Sir, I have a question.
Yes.
So you said it is expected that the rating or like the feedback that the human give is reliable, right? So I basically work in computer vision. So in computer vision, whenever we do human subject experiment, one practice is in between the different images, we may repeat the same image. So if the human is attentive and giving a prompt answer, the answers should match irrespective of how many repetition of the question occurs. So is there any equivalent in NLP? Is there an equivalent procedure in NLP to say whether this human is reliable to believe or not?
Yeah, I think you're asking a very relevant and important question, but I think it is at a more finer grained level than the abstraction that we are talking about. These kind of questions that you're asking, I think will have to, someone will have to worry about them that actually is involved in the process of collecting preference data, right? So typically what will happen is the company that's training the LLM or trying to do alignment will not gather the data itself. It will actually go to an independent contractor, a data contractor, and say, look, I want 100K pairs of, I just want 100K good high quality data that reflects preferences in the, that convey more helpful, or, I'm specifically interested in safety, or I want you to make an LLM that sounds a particular way, for example. It's a style requirement, for example, right? So it's the job of the data contracting company to worry about how to get people in a room, ask them these questions. There may be people who are, fatigued, as you're saying. How do I, take care of that, whether I include everyone's data or I filter it out and so on, right? So these are questions at a level which are at the data collection level. We abstract all of that by saying there is some, in principle, there is a ground truth Bradley-Terry-Luce model. This is R star, let's call it R star, that reasonably explains all these preferences. It will not be a good fit in general for the reasons that you said. Asking a human actually responding in a preferential way to something that's shown in front of him or her can be a very complicated process. It's not clear if we use a Bradley-Terry-Luce model in our head exactly to answer this. Right? It's just a modeling assumption, right? But one can try to go beyond this and make more complicated models of the preference of one answer for another given the question, which are more complicated than Bradley-Terry. I mean, sure, that avenue is always there, but I think in large scale sort of pre-training and fine-tuning, one typically chooses simple models. Yeah, that's the reason they're around, right? So I'm not saying they're a perfect fit at all. In fact, for various reasons, it looks more likely that if you collect preferences from a crowd of humans, it's more likely to be something closer to a mixture of BTL models. A mixture of BTL models is not a BTL model anymore, okay? But that's completely different ball game. Okay, then you have to estimate in the space of mixtures of preference models, right? Yeah. So I think all of these are valid sort of open questions. I think, can you improve modeling? Can you improve RLHF perhaps at the modeling level, right? By learning more expressive models, right?
One question, perhaps a naive one. So how do you choose epsilon? Is that an easy problem?
Oh, how do you choose epsilon is also a bit of a heuristic thing. I mean, there is no clear guidance on. So in practice, what people will do is they will run this process. So they will initialize this maximization at the pre-trained LLM, which is theta naught, and they will keep tracking it as it moves, right? This is basically doing some kind of gradient descent. It will move the theta naught a little bit away, then it will move away and so on. At each point, they will try to keep assessing the KL divergence, okay? They will also keep actually doing different qualitative checks to whatever model is currently produced to see if it is sort of, it hasn't lost its language abilities, right? So at some point, people have noticed that performance falls drastically. If you use a very large epsilon, if you maximize this too much, then it will actually give a higher value of expected R mu, as you know, there's nothing wrong with that, except that that R mu is probably not a very reliable signal in itself. So you want to optimize R mu but not go too far. Okay, so at some point people have noticed that the optimized, quote unquote optimized LLM you get from this procedure is junk, because you just let it move too far from theta naught. Okay, we don't exactly understand why that happens, but the hypothesis is that that R mu is not, you know, a gold standard signal. You just inferred it from some other pairwise data, so it could very well be noisy. And this is something that we will touch upon a little bit more deeper in the rest of this talk, right? Yeah.
Thank you.
Yeah. Okay, so I'll proceed. Feel free to interrupt me at any time if you have any questions. Okay, so this is the RL part. It works the moment you have a reward function. And the step 1's job was essentially to learn a reward function using pairwise data. Okay, so this is sort of the overall loop, the RL part. So we started by asking a very basic question, I think, as you almost pointed to. A reward function, the reward scoring model is a large neural network. It has the responsibility of trying to assign a score to any piece of text. So it's a large neural network. How do you train it? You use data of the order of about 100k preferences at max. A very small amount of literally binary preference data is used. It's like a very ill-specified problem at some level, right? So you have very few data preferences that you gathered, and you somehow want to infer a scoring function that you expect to generalize to all possible reward functions, right? So it seems like a very ill-posed problem. So we wanted to just understand a little more in detail this reward model training process, the step 1 process. So the basic question is how reliable or certain can your reward model that you actually learned from just preference data, how reliable can it be? Is it even stable? Okay, so what do I mean by stable? We did the following experiment. We took a standard data set, in this case it is called some Anthropic HHRLHF. It's a standard data set of a bunch of preferences, about 50k or 100k in number. That's your preference data, okay? And we set up some neural network that is supposed to score, which is supposed to represent a reward model. We did this experiment where we not just trained one reward model, but we just independently repeated the process and trained 10 different reward models. So you have the same data set, let's say you have even the same initialization or maybe a random initialization for the reward model, and then you basically run for the same time a training process to generate not one but an ensemble of 10 different reward models. The natural question was, will we get similar reward models if we use the same data set, right? It was a very basic question. We just wanted to validate whether things are stable or not. Okay, and the 10 reward models that we got, the test for all of them was, we'll give you a piece of text which is like a question appended with an answer. In this case, it is a standard kind of question with a fairly reasonable answer to it, okay? So ideally, reward models should be scoring it fairly high and consistently high. Okay, it's a reasonable answer to the question that is posed. This is the entire piece of text, the red concatenated with the blue, with the green. And the task was, let's get all these different independently trained reward models and pass this string to all of them and see what they think of this, how numerically they score them, right? So it turns out that they have a very wide distribution. Okay. So on this histogram basically plots the reward scores. I think they are between 0 and 10 with the frequency among these 10 reward models. So you can see sort of the distribution in scores. They are fairly wide. Okay, I mean you can repeat this exercise by changing the prompt. You will essentially come to the conclusion that the reward scoring function that they express is inherently extremely diverse. Okay, so they have managed to learn very different ways of scoring pieces of text that are all compatible with the training data, because of course the training is anchored to the training preference data set, but you see this phenomenon, okay, over and over again. So for example, if I had just given you one reward model from this and you are sort of the RL reward optimizer, if you are using one model to optimize your LLM, you might take it in a very different direction than if I gave you a different reward model from this ensemble. Okay, so since different reward models score universally texts very differently, it's not clear what reward you are actually optimizing relative to the preference data set, right? So this is still like an experiment to sort of understand if at all how much variability there can be in learning reward models. just in the step 1 of RLHF. Okay?
Sorry, question.
Yes.
So what is this histogram? When you say it is for one prompt, so you are just asking one question. Is that the way to interpret?
You're asking one question and providing a candidate answer. So you can think in the RL context, it is a RSA. Okay, so it's the RSA for this. Like this piece of text is treated as S concatenated with A. Okay.
But are you not reading too much by this histogram? It's only over S.
It's actually a single, it's at a single state action pair.
I see.
Okay, so but the point is if you repeat this, you change the state action, if you change the piece of text, you will still see a widespread. We can actually benchmark. So you have a large set of test strings. You can actually pass all of these to all these reward models and you can compute the variability of the RSA for each essay and it will still be a high variance. That's what we found. I mean, there is a variance plot we have, but this is just a representative example. Okay?
Sir, I have a question.
Yes.
So rewards are the reward model is trained on pairs of examples. So there is no absolute value to the reward, right? Like there can be an arbitrary offset.
Yes.
And still you can achieve the same loss value.
Absolutely. So that's a very good question. You are saying that it is possible to learn reward models that are constant shifts of each other.
Yes.
Which will literally induce the same preference data set.
Yes.
So that is the natural hypothesis for something that arises like this. But we have done follow-up tests and found out that it's not all translations, right? So they're just not clean translations. These 10 reward models are by no means just clear translations.
So how do you normalize that offset?
How do we normalize that offset?
Like when you want to compare two competing reward models.
When we want to compare two competing reward models, I mean, so one way is to literally plot all their rewards for a bunch of examples, right? And if you see that all of them are sort of just shifted, then you can conclude that they are just a shift away. Okay. One other way is to pick a reference string. You pick one reference string and take differences relative to that. You take reward differences. If these are translated versions, they should actually match up in differences. Differences should be accurate. Okay, so these differences are actually not, they still have variance.
Thank you.
Okay, so that's sort of the check that we did. Yeah. Okay.
But the reward could be genuinely random, right?
The reward.
10 people, their opinion about
Yeah, so that's a good, that again goes back to, how do people actually respond, but at least we know that in these data sets, these are not highly controversial questions where, a significant fraction of the people will prefer one to the other and the other to the one. They are fairly clear-cut sort of, at least the responses that are provided in the data set for people to rank are fairly clear-cut. Actually, so I should be a bit more careful. A fraction of responses in these data sets is actually very noisy, as you say, okay? So in fact, these questions are whatever questions they are, and there are literally two very similar looking answers for the same question, okay? So there's a significant fraction of such contamination in these data sets that actually, for which you have literally random responses, as you're saying. So one has to be careful, like people might actually sometimes filter out these obvious, like very similar answer kind of pairs, where you don't get any information by looking at which is the winner and which is the loser, because it's literally random. Okay, so you have to somehow do some filtering to get higher quality preference data. Okay.
Sir, my question was kind of a follow-up from that question. So where the discussion was like there can be a translation, that's just a simple transformation between different reward models, right? So my question is more like, so let's say this was the study on English language, so which is a high resource language. So yeah, you have more online data as well as more people who consume the data in that language. So if you, let's say, do it for a low resource language, would still that problem not be there, like this translation problem? Can it pop up in a low resource LLM?
It's certainly possible. I mean, the mathematics certainly allows for it. I mean, all you have to notice is that Bradley-Terry probability formula is invariant to translations of the reward function. So you could have the same problem in any other language application. Okay. I mean, we are just dealing with any, like the space of all strings, so which includes in principle, you could tokenize low resource languages and put them in the same space. So the problem still exists, I think, right? Right. So there are a bunch of reasons actually that you could posit for why this, these reward models might be very diverse in what they learn. Inaccurate is perhaps not the best possible term here, but diversity in learning scalar reward models could be explained by one of several factors. So I'll just mention some of these that we thought about. The first thing is what we have discussed already. It's not obvious that a human perfectly uses this BTL kind of model to express preferences. There may be no ground truth. Okay, we are trying to forcibly learn a reward function using this BTL kind of preference model, but it might just be an inherently misspecified problem where the actual distribution of preferences is very complicated, and it cannot be matched by any representative, any realistic BTL model that we might come up with, right? So there may be a representational mismatch problem. The second issue is that, as I said, these reward models are typically learned with relatively much fewer data, right? There's just 100k preferences, of that scale, and you expect a very complicated reward model R mu with a lot of parameters mu to be learned with a few data, and this inherently creates some stochasticity or diversity in the outcomes for training, right?
Sir?
Finally, there is this training process itself, right? How do you actually train a reward model? The standard sort of prescription is get your data set, you have this BTL loss function, the maximum likelihood loss, and then pass it through some form of SGD or gradient descent with batching, right? With inherent stochasticity. It's stochastic, training is stochastic, training is inherently non-convex. You're training a reward model which is a neural network. So it's possible that the outcomes could actually go and sit at very different places, right? So it's not, in hindsight, very surprising that you get an ensemble of reward models if you ever care to repeat the experiment of training a reward model, right? So I think there wasn't much attention on what happens in the reward model training process in the sense of variability. People just assume that you train a reward model once, take it and then run with it, right? So we wanted to study this phenomenon of what you actually get at the end of the day a little more carefully.
Sir?
Yes.
Another question that I just had was these models that are being designed.
Yeah.
So is it like let's say I'm not sure aware of the details though, but I presume maybe some BCI EEG signal was analyzed, and that's how we understand how humans think, right? Like, is that am I right? And
yeah, I mean, I think this is sort of outside, my pay grade. I mean, I think you are asking questions about, are there models, let's say neurological models of how humans perceive data and then respond, right? I don't know the answer to that. I don't know if maybe the Bradley-Terry Lewis maybe has actually a neurological connection or something. But it is actually a pretty expressive and simple model and it has some alternative interpretations that are particularly nice, right? You can actually derive the Bradley-Terry model. One other way of deriving this preference model, which is Bradley-Terry, is by assuming that everyone actually scores it first, with a deterministic reward function in your head, and then you add some noise into, you add some noise internally, in your thought process, and then you just output the winning reward after the noise is added, right? So there is an interpretation of Bradley-Terry in that way, which probably may be closer to how humans actually think and cognitive processes. I'm not sure. Okay. And just to sort of convince you that this reward model training is actually done not to completion, so there are these two very representative papers in language modeling. I think one is from the OpenAI team. So the left one is from the OpenAI team. There was the first paper that actually talked about RLHF. So you see the highlighted phrase there. We use a single epoch to avoid overfitting to the small amount of human data. So the small amount of human data is the preference data that they're talking about. And this paragraph is about how they trained the reward model. We use a single epoch is literally saying that we touch every pair in the data, preference data, exactly once in the training process, right? So it's a very small, almost no reuse of data, and it's not really optimizing that Bradley-Terry loss function to train. It's a very incompletely trained reward model. For reasons that are intuitive, they say we don't want to overfit to the small amount of preference data, so we are sort of stopping the training early. But as you may know, that also gives rise to variability in the outcomes, right? The second paper is from the Llama technical report. Llama is one of the most popular open source models released by Meta. In the same reward modeling section, they just literally follow the same prescription and say we train for one epoch over the training data, the reward model. In earlier experiments, we found that training longer can lead to overfitting. So basically, the reward model that you learn does not really make good sense. Okay, so the reward model training is deliberately undertrained, but our observation is that it is very likely to produce variable outcomes. Okay, so the central problem that we wanted to sort of study a bit further is that if you just train a single reward model with very few passes over a preference data set, it can actually be an unreliable yardstick in the sense that if you retrain this reward model, you could get a fairly different looking reward model. And the problem is that this reward model is going to be used downstream to optimize the policy. It's going to be treated as a reward signal, right? So if that reward signal itself is unreliable, then what do you have to say about whether you are actually improving the policy in the RL phase, right? So we could be optimizing a junk signal or a pretty unreliable signal of reward, and this is also in the literature called reward hacking, when you sort of chase a signal that you believe is representative with your task, but which really doesn't really have a very accurate resemblance to the task that you actually want to achieve. Okay. So it may be useful to sort of step to a more theoretical lens. So a very simple representation of this problem that I just told you about, you can think of it in the context of a multi-arm bandit. A multi-arm bandit is a Markov decision process with only one state. So just imagine, so in the context of LLMs, you can just imagine that there's only one question in the whole world for the LLM, and there are only 3 possible answers that the LLM can give out. Okay, so the LLM is a policy, it's a distribution over 3 candidate answers. In this case, it's a three-armed bandit. So there are 3 arms, and the vertical axes represent numerical reward scales, right? So bottom is low and top is high. And let's say that I gave you a multi-arm bandit policy. The base policy for my multi-arm bandit is that p theta naught, which is just a uniform distribution 1/3, 1/3, 1/3 on each of these arms. Okay, and that's my base policy. I want to try to improve it, and I tell you that look, I estimated these rewards for these 3 arms through extensive pairwise comparisons or whatnot, right? So I have these reward estimates R1 hat, R2 hat and R3 hat, right? So if these are my reward estimates and I'm telling you, look, try to help me improve the policy by changing these policy probabilities for these rewards, right? What is, I allow you to change these rewards by only an epsilon amount, right? What is the most direct way to sort of, you have epsilon budget for change, well, in which probability will you put that? If these are the true rewards, right? Which arm's probability would you decide to increase? It's arm 1, okay. So if these are actually the true rewards, to maximize, to improve the expected reward, you should just put whatever budget you have, for improving the policy only on the arm that has the highest reward, okay. So that's sort of a it's a no-brainer sort of, it's a no-brainer kind of answer. However, the situation is a little more complicated if I told you that, I have not only estimated these rewards R1 hat, R2 hat and R3 hat, but I have also estimated in some sense, let us say I have estimated some amount of variation in the rewards of each arm, right. So I tell you that the reward of the first arm can be R1 hat plus minus a wide interval, which denoted by those brackets. R2 hat is fairly well estimated, so you can imagine that R2 hat is literally going to be very close to the true R2, and R3 hat has the same deviation profile, right. So the picture here is that you can't trust R1 hat as much as you can trust R2 hat and R3 hat, okay, and you have to live with this. You can't go and collect more data, you can't reason more about what the reward function is going to be. This is the picture that I portray to you, right. With high probability you can be anywhere in that bracket, okay. So in this case, if you started with a uniform policy 1/3, 1/3, 1/3, it would, depending on your outlook, if you wanted to be, safe or conservative, right, or if you had a bit of a conservative outlook, you would say, look, I will try to actually I will find a more robust solution, which is to actually increase the probability of arm 2. I will keep the probability of arm 1 unchanged. I don't want to nudge the policy for the arm 1 part, but I know that if I increase the if I increase the probability for arm 2 and then correspondingly maybe reduce for arm 3 because they have to sum to 1, then I will at least be guaranteed an improved reward, which I know is true, right. I'm not sort of messing around with arm 1 because it's uncertain. I don't want to optimize my policy in the area that, in reward regions that I'm uncertain about. Okay, so that's sort of like a simple takeaway from this example, right? So if you understand this, then sort of our prescription sort of is a generalization of this, right? At least for this very simple scenario, okay? So our proposal is, we said, let's rethink how you do policy optimization using a reward function. So the standard way is you take a reward function r hat, at least in the standard pipeline, and then you say, look, I will improve my expected value of r hat from the policy theta 0 to a new theta, such that, I have a global KL divergence constraint, right? So that's the vanilla RLHF problem. Now we want to sort of augment it or modify it to say, don't move. If I give you additional information about the uncertainty or the standard deviation or the variance of these rewards, can you use that to sort of be a bit more conservative and optimize the policy and not move far in directions that the reward model is not confident about or where it has high variance, right? So the idea is to translate this prescription to some form of mathematical optimization problem, okay? So what we sort of at a high level propose is if you are able to somehow benchmark or understand the uncertainty in the reward modeling process, literally we would like you to give an interval for r hat SA for every SA pair, then use this uncertainty in a wise way to sort of do the downstream reinforcement learning optimization such that you are at least guaranteed some baseline amount of improvement, right? So that's sort of the proposal here. So there are two versions of our sort of conservative RLHF sort of optimization problem, RL procedure that we propose. One is sort of a little more application or user friendly, it can immediately be implemented. So recall the original problem of RLHF where you said, I just want to maximize the expected R mu that I had from my step 1 subject to a KL divergence constraint. Now that KL divergence constraint you can actually expand and write it as an expected value over probability into log likelihood ratios. All we are saying is, put a weight in front of the, wherever you write the KL divergence, P log P, you put in an additional factor which is the sigma square, the amount of variability that you have measured or anticipated for the reward for the text QA. Okay, so hopefully if you have a measure of uncertainty that you can derive from your training process, which is represented by sigma square QA, you put that sigma square QA in the distance in the KL divergence constraint in this explicit way, so that the net effect is that if you have a question answer pair where there is a high amount of variability, this sort of thing will implicitly prevent the probabilities from changing too much for the specific answer A at question Q, right? So it has the effect of sort of putting a higher penalty on moving your policy probabilities for that particular question answer pair, right? So it takes care of sort of self normalizing your amount of movement. Okay, so this extra term, if you actually don't have that term, it's the standard RLHF objective, the policy optimization objective. It turns out that we can sort of make a more theory friendly version of this where you replace KL divergence by a different measure of distance on probability spaces, which is just a simple L2 distance. Okay, so all I've done here is it's the same equation but with the KL divergence replaced with a much more tractable sort of divergence that we can analyze, which is just a simple L2 norm square. So the sigma square here again has the same effect of preventing a large movement from theta 0 to theta whenever that sigma square term is large. Okay, and why I call this theory friendly is that well, there are several reasons. For example, in fact the previous version, the user friendly version itself is actually in the tabular case, in the case where every prompt and action can be represented by the LLM, just as was commented that you have an explicit answer for the policy optimization. If you put a sigma square in there, it just reduces to basically finding the optimized policy, not with respect to just the estimated reward, but the ratio of the reward to the variance, which is often called the Sharpe ratio in finance and so on, right? So you can interpret this whole proposal as trying to reach, in an ideal sense, the policy that not just maximizes purely for reward, but it maximizes in some sense towards the Sharpe ratio, which factors in uncertainty along your reward scoring function. Okay, So I'll maybe just stop in 2 minutes. So it turns out that we can make sort of a toy theoretical framework to sort of demonstrate that our variance aware prescription is actually more conservative in the sense it enjoys lower risk of producing a worse policy at the end of the day than the vanilla approach, right. So of course we assume that in our analysis we assume that there is a ground truth Bradley-Terry model that is actually generating preferences. So the actual reward function is some R star which is unknown, and we also assume that using finitely many preference data and abstracting the entire reward model learning process, the step 1 process, we abstract it using a reward model R that can be modeled with a standard like a Gaussian distribution, right, a multivariate normal distribution whose covariance accounts for the fluctuations of the training process. The reward model's training processes are abstracted using some variability represented by a Gaussian covariance matrix sigma. And we are able to sort of show like theoretically that if you use the variance aware RLHF procedure which with the sigma square QA weights there, then it's equal, the variance aware RLHF has the effect of minimizing not the R hat but actually a lower confidence bound on the R hats, and so that's effectively what it is doing. Okay, so we can prove such results, and we can ultimately even show that we in fact achieve a provably safer policy in the sense that if you do this variance aware RLHF, then you are a little less prone to actually significantly worsening the initial policy, right. So there is a small chance that if you use a single reward model and do vanilla RLHF, you might actually get a worse policy than the initial policy, than the base policy. But using the the variance aware formulation actually reduces the probability or the risk that you will actually degrade compared to your original policy. So in some sense it's a conservative statement. It says that you enjoy lower risk after optimizing. You could also enjoy lower reward after optimizing. So it could be low risk, low reward, but certainly we know that it is lower risk, right, under this toy model. So we actually took this to, with the limited amount of resources we actually implemented this variance aware RLHF. We trained a relatively small ensemble of reward models on actual text, and we used it to actually optimize again a relatively small language model. I think it was a GPT-2 class model, and we actually see sort of the low risk kind of prediction pan out. So this figure illustrates that method 1, which is vanilla RLHF. This is a histogram of the rewards achieved by the quality of the final policy relative to the base policy, and you can sort of see that the red training outcomes which are from the variance aware RLHF are sort of concentrated over a smaller range, or the variability in those rewards that they produce is much smaller and more robust than the one that the vanilla RLHF procedure achieves on the same setting, right. And so yeah, there are sort of similar, this is the theory plot, and this is the sort of the little more messy practical plot where the base model has this particular reward profile, and method 1 is the yellow method is the vanilla RLHF, and the red method is our little more variance constrained RLHF proposal, which actually improves the risk profile of the model that you get out of the final RLHF procedure. Okay, so this is an initial sort of stab at this problem. Of course, one has to realize that all this works only if you can reliably quantify some kind of uncertainty in your reward model training process. So you not only have to sort of train a reward model, you also have to find some way, clever way of trying to interpret how confident that reward model is about its own reward prediction, right. So sort of a very basic approach that we used for our experiments is just ensembling. If you have the capacity, you can train not one but multiple independent reward models, and you can sort of use them as some kind of empirical distribution to find out a measure of variability. But this is easier said than done, especially for very large reward models, right. So those are open problems in sort of uncertainty estimation of neural networks. In the future work, this kind of approach can also be extended to other fine-tuning approaches. For example, there is a alignment method that completely sidesteps training any reward model. It is called DPO, direct preference optimization. It's actually quite a fascinating proposal. It says don't train a reward model separately, just give me pairwise data and I will help you improve your initial model, initial LLM to a final LLM. But you could imagine that the same problem persists there. With very few preference data pairs, what's the guarantee or risk that actually doing DPO will actually produce a much better policy, right? There is a certain amount of risk that it might actually fail. So being conservative potentially could be developed for another pipeline like DPO. And so this remains to be seen how you can do this. I think one can also try to reason about uncertainty. If you don't do explicit RL in the second stage, but if you do like best of n sampling, you just use sample based or Monte Carlo based techniques to improve your policy. You still have the issue that your reward is sort of highly variable. So you could incorporate uncertainty measures to design more conservative procedures. Okay, but the moral of the story is sort of you have to be aware of how much variable your reward signal really is, and not sort of optimize too much for in directions where the reward model is actually underconfident. Okay, so so that concludes my talk. There is a preprint you can find on archive at this point. Thank you.
Yeah, hi sir. I have one question. So how to measure the confidence of the reward model here?
It's sort of a big question actually. So the only I think way that I know to do it, in general is you have to do what is called ensembling, right? So exactly the thing we did. We were able to sort of train in parallel not one but many independent replications of that reward model. Yeah. And if you look at that, then you can sort of look at the variability of what this ensemble produces over all your text as a measure of the variability of the training process, the reward model training process, right? So ensembling is sort of the obvious idea. One could probably try to make do with then the question is what is the size of the ensemble you have to take, right?
Yes,
and
yes.
that has computational costs.
Yeah.
So it may be possible perhaps to take small ensembles and somehow try to in fact learn the uncertainty function perhaps, but it's not clear whether it will generalize properly and so on. Yeah.
Yeah, okay, thank you.
Yeah, it's a good question.
Please go ahead.
Yeah, my question would be naive. So from the examples given, it appears to me like sort of a sentiment analysis is first required. Let's say we don't want the question to be answered like how to prepare a bomb or things like that. So and that is one perspective. And second perspective is like when humans need a domain knowledge to give a preference.
Yeah.
Rather than the clustering would have been more. Domain independent. For example, given an answer, let's say if I see this is suicide and things like that, and then I can do a sentiment analysis first, and which means cluster the answers, and then do the preference and the second level. Would that maybe that reduces?
I suppose broadly what you are hinting at is some kind of pre-processing
Yes.
of the questions or answers before you actually submit them for preference.
Instead of considering all the answers for preferences.
Yeah.
Filter out using the sentiment and then use, if I say that this question is like a positive sentiment, I do the ranking only for those answers for that question rather than ranking completely all.
You could do that possibly, but ultimately you will finally have a ranking at the end of the day. You'll still have ranked data and you'll have to use ranked data to actually, then you have to infer an anyway reward function at some point. Possible. Yeah, it may be possible. Yeah. There could be any number of approaches you could take to try to reduce the variability in your preference data. So that could probably solve a large part of the problem. I agree. Yeah. Yes.
No, just 1 minute. Just use the mic. It's on YouTube, so we want the question to be audible.
Okay, so you have an ensemble of, I'm just looking at the empirical experiment. So you have an ensemble of reward models, presumably some Bayesian ensemble or a deep net ensemble to get an uncertainty measure.
Yes.
So my question is, we had that, did you try LCB directly in the reward objective and just do the normal KL stuff? Would that have done better, or because it's like an offline RL problem, right? Because the data
Yeah,
set
so
is
in fact, so in fact, I think it is somewhat equivalent in some sense. What we are doing is something like this, okay? You can reinterpret it actually as, maximizing, you can cast this in terms of R hat minus an LCP.
okay.
It's exact, I mean, so that theorem that I presented literally says that, okay? It actually says that, the right hand side, which is the R hat minus an LCB, if you reinterpret in the constraint optimization form, you are taking this term down in the constraint, the last term, and then you
Thank
get
you.
this.
Yeah.
Right, so it's effectively that.
Okay, thanks.
Good.
Yeah, I have one question.
Yeah.
So why is it called RL? I don't see any MDP in the background.
Okay, that's a very good question. To me, at least, the RL flavor here is only coming. It's more like a contextual bandit. There is no MDP with a state evolution. If you look at, so it depends on your view. If you look at it as if a state and response is entire string gives rise to a string, right? The Q gives rise to an A. Another question answer pair has no relationship to the previous question answer pair, right? So it's literally there is no state evolution here in this case. But there is a different view where you actually think of a string as a sequence of tokens. Okay, so in that sense, the R for a Q and A is to be interpreted as there is an MDP, which is a token level MDP, right? One string gives rise to another, the next token, next token, next token. In there, the dynamics are according to the LLM, the P theta LLM. And you get this reward at the end of the answer, right? It's like a sparse MDP where the dynamics, transition dynamics are given by the language models, generations, and the reward is obtained at the end of the trajectory. So Q and A together constitute a trajectory, and you get a reward at the end of the trajectory, right? But it is often a bit convoluted to imagine things this way, right? So I came to a similar conclusion that the RL here is not really at some level. It's not a state dependent.
Yeah, you are doing token by token, not for that.
Yeah, if you look at it at a token by token level, then you can actually imagine this to be an MDP with state change. But
But then you should take into account the value function, right? You are not.
That is true. That is true. So there are now some prescriptions, very new prescriptions of doing RLHF with the Q function rather in that view, rather than the R function.
Yeah.
So in this view, it is purely a contextual bandit. But you could try to do it with Q functions at the token by token level. But in that case, you could probably take that view and do things. Yeah.
Another just comment.
Yes.
Maybe a decade or two back, there was some work on BTL model.
Okay.
Starting with a paper by Negavan O and Devrat Shah, and some follow-ups.
Yes.
Right. So that's not being used here.
It's a great question, and it's something that I only recently learned. Exactly this paper. So in my perspective, so they have a very different approach to learning a Bradley-Terry model. So the summary of that paper, as I see it, is that a very default way of, if you are given preference data and I told you they came from a BTL model, one way is to just do maximum likelihood. That's the default thing that everyone does in RL here.
But
ML here.
see what they do is,
those people do a spectral algorithm. They actually set up a random walk and then.
See, there's a series of articles, including one by me.
Yeah.
What you do is you assume that the probability of preferring J
Yes.
over I.
Yes.
So say Pj, comma I.
Yes.
Has this form e to the something normalized.
Correct.
And you plug in that probability by your estimate thereof,
Yes.
empirical estimate, and solve the equation. And it's solvable iteratively.
Yeah, I think it has relationships to a spectral, like sort of a stationary distribution of a Markov chain or something. Anyway, in any case, it's a different estimator for a BTL model. So it is also an interesting open question whether you can come up with an entirely new RLHF process where you replace maximum likelihood, the step one, with any one of these estimators. The only, I think the question here is, will it scale to really large, these are sort of really large state action spaces or action spaces. So I think all the analysis has been done for the tabular case for these Bradley-Terry tabular models. I think an interesting question to generalize it.
You end up solving, at least in one variant, you end up solving a linear system. So even if it's large, it should be.
Yeah, so I think it might be attractive if one can justify that it is computationally, competitive. Yes. So I think certainly these are very interesting directions. You replace, like there are any number of estimators for BTL. Maximum likelihood is not the only one.
Okay, maybe in the interest of time, we can take other questions offline. On behalf of the organizers, which is me and Professor Bhatnagar, I would like to hand over a token of appreciation. So maybe we can go over there.
Thank you very much to the organizers.
Thank you. So with this, we come to the end of the workshop. If I'm not wrong, there is tea and coffee outside. Okay, so we can break out. Thank you.